So let's think about this. So when we're looking at oxidation states, right, we need to go ahead and we need to find those oxidation states. So let's look at the compound first and we'll go from there. So let's say that we have something like tungsten with 4 chlorines. And so what we would like to do is we would like to determine the oxidation number for each of those elements. Now, when you do oxidations, each element should get their own, right? What that means is that if we have a reaction or if we have a compound, we have to be looking at the element. We can't really split up our oxidation numbers for each of those elements like inside of it. So it's not like one of these chlorines is going to be something and the other chlorine is going to be something else. If it's in that same compound, we're assuming that they're kind of behaving the same. And so what oxidation number do you guys get for tungsten? And what oxidation number do you guys get for chlorine? What do you guys think? You can either chat it or you guys can unmute yourself and you guys can talk. Either one. Any thoughts about how we find this? So where do you guys start? If we have this problem, we have a compound and we would like to find the oxidation numbers for them, how do we start this? So you are right that when we look at a compound, all of the oxidation numbers are going to be equal to their charge. So in this compound itself, do we have any charge on it? For this compound, do we have a charge?
Yes.
What would the charge be for the compound?
For the whole compound itself?
Yep, for the whole compound.
0.
So is that a charge?
No.
No. So in this case, we don't have a charge on it. It's a neutral compound, but you're right that all of their oxidation numbers are going to add up to be 0. And so that's kind of what we're looking for. Now, when we do like an ion, then that could be something different. So between our tungsten and our chlorine, is there one of them that we might know their oxidation number, what it should show up as?
Chlorine should be -1.
Right? And how did you know chlorine should be -1?
Because it generally has a charge, a -1 charge.
Very
when
good.
It's ionized.
And when it's ionized, it generally has a -1 charge. And so that's a good place to start. And so when you're looking at your oxidation numbers, in your book, they give you a table of rules of what you need to follow in order to kind of piece it together. And it says things like oxygen is normally a -2, or fluorine is always a -1, or hydrogen is a +1 when it's with a nonmetal, and -1 when it's with a metal, right? And so there's these different rules that you can kind of piece together for it. One of the ones that I like to use is when I think about my compound, what I'm looking for is what ion is the most common. Because a lot of times they're going to take on that charge. So like how chlorine almost always forms a -1 ion because it's a nonmetal. It's very close to being a noble gas. It just needs to pick up one more electron. Tungsten, on the other hand, tungsten's a transition metal, and so we don't know what kind of ion it's going to form. We don't know the charge of it. And so that's kind of how I go through and I figure out which one I might want to start with. Now, the hard part is that sometimes not all of those elements get to be their most commonly formed oxidation state. right? And so that's why there are these rules that you would have to follow about who kind of gets priority in that case, right? So if you have a fluorine and a chlorine both together, if only one of them can be -1, it's going to be fluorine, right? And so there's some of those rules that help with that. But yes, so we have our chlorine there as a -1. And now how many of those chlorines do we have?
4.
Yep, we got 4 of them. Nope. I'm going to go ahead and clear out some space here. All right, so we have 4 of them. And so one of the ways that I like to do this is when I set up an equation. And so my charge is always going to be on the right-hand side. And then I say how many of each element and and how many atoms of each element I need. So it's kind of like my 1 tungsten and my 4 chlorines should add up to 0. So if I have my 1 tungsten and each of my chlorines is a -1, then I can kind of get this to my 1 tungsten minus 4 is equal to 0. And so what should the charge of my tungsten be? Very good. It should be a +4. And so with oxidation numbers, the important part is you're kind of looking at those different pieces of that compound and then just work with each of those reactants at one time. So let's jump to another one. Let's look at something like bromate. So BrO4 minus. And so we are looking for the oxidation number of bromine and oxygen. So I'm going to give you guys a moment, and then you guys can start to write it in, right? Write in your answers. What should the oxidation number be for bromine? What should be the oxidation number for oxygen? So looking at this, now that we started to get some answers coming in here, are you going to start by identifying the bromine, the Br, or are you going to start off by identifying the oxygen? Which one of those oxidation numbers do we know more about? We should start off with the oxygen, right? And so there's a rule about the oxygen, and that's that the oxygen is almost always a -2 charge, right? It can be a -1 or it can be a 0, right? But it's almost always a -2. So we want to start with that part. Now, with our oxygen being a -2, we can set up our equation here. And so we should have 1 bromine. And how many oxygens do we have? 4 oxygens. And then what's the total charge of our compound here? -1. So that means that we're going to have 1 bromine that should be equal to almost all of the charge of those 4 oxygens. And so we said that the oxygen should be a -2. Sorry, too many minuses there. -1. And so we get bromine -8 is equal to -1. And so our bromine should become what oxidation number? It should become a +7. And so that's kind of how you work through and you figure out all of your different oxidation states. That can get more complicated because we could have something that has more than just 2 elements. So we could have something like K2CO3. And we might have to find all 3 of these oxidation numbers. So you can do this in the same way that we've been doing the other ones by setting up our oxidation state equation. And so our charge in this case is going to be 0. And we should have 2 potassiums, 1 carbon, and 3 oxygens. Or in a special case, if you're looking at here, is there any polyatomic ions in that compound? Right? And what's the name of that CO3? Carbonate. So we can kind of split this potassium carbonate into 2 parts. We could split it up into a potassium and the carbonate. Now, what's the charge of that carbonate? -2. And so if that carbonate is a -2, and we have 2 of those potassium ions balancing it out, what should the charge of our potassium be? So each individual atom of that potassium, not all of them together, should be a +1. So if potassium needs to be a +1 ion in order to balance out the carbonate one, the potassium oxidation number should be what? It should also be a +1. So we can kind of use those polyatomic ions to help us split them apart. And so then we can deal with it kind of in a 2-step process instead of doing all of them at once. But we'll also do them all at once so you can kind of see the difference between them. So now that we've gotten our potassium out of the way, now we can focus on our carbon and our oxygen. Now, do we know the charge of carbon, or do we know the oxidation number that oxygen takes on? Which one of those are we more confident with? Our oxygen, right? And so we start off with that one because we know the most about it. Our oxygen's almost always that -2. So we can use oxygen for that -2. And then what we should do is now piece together and figure out our carbon. And so in this case, what oxidation number does carbon need to have? It needs to be a +4. Very good. Yeah. So we have a +4 and we have a -2. So that's what it looks like if we do it in a two-step process. If we wanted to do it all at once, yeah, we're actually just going to make a little bit of space. If we want to do it all at once, then what we want to do is start to piece together the parts that we know. And so we know oxygen should be a -2 charge. Then we're looking at potassium. And so we know that the oxidation state of potassium is almost always a +1 because it's an alkali metal, right? Alkali metals, they normally lose their electrons when they form a compound. And so that's how we know that it's going to be a +1 because it needs to remove one. It needs to lose one electron. So we got +1 there with our carbon and our oxygens. So this becomes a +2 plus whatever carbon's one is, -6 equals 0. So that becomes +2 plus carbon is equal to 6. Carbon is equal to +4. And so that's how we can find it out all together. So it just depends on which one makes the most sense to you. I generally, if I can find a polyatomic ion that I can see in there, then I use that to break it apart. If I don't, then I have to piece together my other parts. Okay. Any other questions on finding the oxidation numbers? We will do some ideal gas law problems, but we're first going to finish off this oxidation reduction. We're going to do one where you guys have to find, I'm going to give you a chemical equation, and then you guys are going to have to write the half reactions. So just give me 1 second. I want to make sure it's balanced before I give it to you guys. Okay. So for this one, we're going to split you guys into two groups. So that way you guys can kind of work your way through with this one. What we want to identify is we want to figure out our half reactions. So we have our oxidizing and we have our reducing. Now for oxidizing, what does that look like? If we are going to be oxidizing, are we gaining electrons or losing electrons? What do you guys think? If you're oxidizing, are we losing electrons or gaining electrons? Right? Oxidizing is losing, right? So remember, Leo the lion goes grr, right? What that means is oxidizing loses electrons. And so if it loses electrons, does its oxidation number go up, like become more positive, or does it go down, become more negative? Are electrons positive or negative? So if we lose negative things, are we going to become positive or are we going to become negative? Positive, right? So losing electrons feels weird because our oxidation number is going to become more positive. Reducing is when we gain electrons. And because electrons are negative, then we are going to become more negative as we gain more of them. So what we want to do is we want to take this. We need to find out all of our different oxidation numbers first, And then we're looking for who is oxidizing and who's reducing. Once we have that, then we can split that into our half reactions. So what I'm going to do is I'm going to split you guys into two groups, and then I'll check in on both of you guys for your breakout rooms. So that way you guys can start to work on each one of these, right? So I want you guys to go through, find your oxidation numbers, and then we're going to create those half reactions. So your goal in your breakout rooms is just to figure out who's oxidizing and who's reducing. You don't have to write those half reactions yet, but you do need to find all of the oxidation numbers for the compounds. I guess really the elements in each compound. And then we should be able to identify who's oxidizing and who's reducing. Okay, so there are a total of 5 compounds there. So you have a bit of work that you guys need to do. Does anyone have any questions before I split you guys up? Okay. Now, make sure that you take a picture of this or that you have this equation written down, because once I split you up, someone has to have it. Okay. Good luck. So what oxidation number did you guys end up with for manganese in this Mn2O3? Yeah. We should have that one as being a +3, right? Remember that it needs to balance out our oxygen. Oh, sorry, not +2, should be a +3. And then the oxygen should be the -2. All right. What did you guys find out for that carbon in CH4? What oxidation number do you guys have for that one? Very good. So we should have this as a -4. And that's because for the hydrogen in this case, what's the oxidation number for our hydrogen? A +1. Right? So remember, hydrogen is going to be a +1 when it's mixed with a nonmetal and a -1 when it's mixed with a metal. And so on this second side, our CO2, what oxidation number do you guys get for your carbon? +4. And our oxygen? -2, very good. Mn in H2. So the manganese in MnH2. What charge did you guys get? 8 seems a little bit high, right? Remember that it's not all 4 of those MNs all together. We have to talk about it each by themselves. And so this one should be a +2 because each of those hydrogens are going to be a what charge? -1. So the important part is that when you guys get these coefficients in the front, it actually doesn't impact your oxidation numbers at all. It's going to impact how many electrons are transferred, but it doesn't impact the oxidation number itself. Right? Looking at H2 here, what did you guys get for your oxidation for hydrogen inside of H2? Did everyone get a +1 for hydrogen all by itself? Because the issue that we have, right, if it's H2 and this is a +1, then that would mean that our charge would have to be a +2 in order to get that to balance. So our oxidation number can't be a +1. It needs to be a 0. So remember that all elements in the elemental form are going to be a 0. So sometimes that's the easiest one to start with, is if you ever see an element by itself, then put it as a 0. Now, let's look at our oxidations. Who's oxidizing? And so what did we decide? If we were looking for something that's oxidizing, what's happening to our number? Is it becoming more positive, more negative, or staying the same if we are oxidizing?
More positive.
More positive. Very good. And so which element is becoming more positive?
Carbon.
Carbon. Carbon's going from -4 to a +4. So it's really oxidizing. And so it is losing how many electrons?
4. 4.
What do you guys think? Is it just 4? Because each electron is a -1 charge. And if we go from -4 to +4, is that a change of only 4 electrons?
Oh, it's 8.
It's 8, right? We need 4 electrons to get us to 0 and another 4 to get us to +4. Excuse me. So we are losing a total of 8 electrons per carbon. So that's a lot. Is there anyone else that's oxidizing? No, I don't see anyone else that's oxidizing. What about reducing? What element is reducing in this equation?
Manganese.
Manganese, right? We got +3 going to a +2. And so this one is gaining. And how many electrons is it gaining?
1.
1 electron for each manganese, Mn. Is that the only one that we have that's reducing?
No.
No. Who else is reducing?
Hydrogen.
Hydrogen, right? Now, is it reducing in both cases? Is it also reducing to that H2 as well as into that MnH2?
Yes.
Yeah, right. And so each one's a little bit different. So when it goes into the hydrogen gas by itself, it's gaining 1 electron. When it's going into that compound, how many electrons is it gaining?
1.
So when
Oh,
it
no,
goes into
2.
MnH2, it has to gain 2 electrons. All right. So,
Professor?
Yep.
Do we also need to know how to write out the half reaction as a formula?
So we are going to get into that part.
Okay.
Okay. So from here, we're going to write out the half reaction when it oxidizes. So the oxidation one. I'm going to do the one for the reduction. All right. So one thing that I've done in order to kind of simplify this is I'm going to make both of our reactants aqueous. And we're going to make our product, the manganese hydrogen, or manganese hydride, we're going to make that aqueous as well. Just so that way we can split them up into the ions and make it a little bit easier to work with. So for our oxidation, we really only have to worry about that green connection, which is our CH4 going to our CO2. Now for that CH4, we're going to split that up because it's aqueous, and we're going to pretend as if we had our carbon separated from our hydrogen. So that's CH4. We're going to pretend that this is a C4 plus, or not 4 plus, 4 minus, and the hydrogens are plus ones. So oxidation reaction is looking something like this. Keep writing the minus. Four minus is aqueous, and is going to CO2 as a gas. And we said that it was going to lose 8 electrons. That oxygen is coming from our manganese oxide. And so that can be our O2 minus. And if we wanted to balance that, we would need 2 of them. So does our equation look balanced so far? Just within our carbons and our oxygens? Or do we need to add any more pieces? So we're balanced right now, right? And so that's kind of what we're looking at. So basically for a half reaction, what we're trying to focus on is only the stuff that is actually losing those electrons. So that's why we wanted to split up that carbon from the hydrogens, because the hydrogens are involved with the reduction side of the process. So it was going to be a little bit tricky to include both of them in both sides. And so that's why I wanted to just split them apart and make them aqueous. Now on your quiz or your exam, it would be a little bit easier. It wouldn't be as common that we would have one compound that's doing kind of both. But that's kind of where we are for today, right? So when we're doing our reduction, we know that our manganese is reducing. And so what should that charge of that Mn be as a reactant?
+3.
+3. And then from there, we should also be reducing our hydrogen. And so what should the charge of our hydrogen be that's reducing?
-1.
So on the reactant side, is it a -1 or a +1?
+1.
+1. Now, when we get to the other side, we want to put in our compounds that involve them. So we have our Mn2. Oh, sorry, not Mn2H2. That's just MnH2. And so we have our Mn, and it's going to be a 2+ charge because it's in the +2 oxidation state.
Professor,
Mm-hmm.
for the oxidation reaction, you kept the coefficient on the oxygen, but you didn't keep the one from the carbon.
That's because for our carbon, do we need more than one of them so far?
Oh yeah, if you added the coefficient, it would multiply the charge, would it?
So right now, what we haven't done is we haven't balanced it for like the entire reaction, but we have balanced it within its half reaction, right? So looking for carbon going into CO2, that's why we have to have 2 oxygens, is because that CO2, if we make 1 molecule of it, it still needs 2 oxygens. Later on, what we're going to do is we're going to balance them based on how many electrons get transferred. And so then we're taking into account the fact that we're going to need more of them. Okay? And so we didn't want to put a 3 here, because if we put a 3 here, then this has to become a 3. Then our electrons lost would have to go up as well. So we're kind of just trying to make the simplest version. We're not just pulling it in from however many we had up there.
Hmm.
All right, so our hydrogen in this case is going to be a 1 minus. And then we're going to have our hydrogen gas, which is going to be a 0. Now, how many hydrogens should we have with that 1 minus charge? If we're trying to take one of those manganese, how many of these hydrogens should we have?
Can you repeat the question? I'm sorry.
So we are trying to use one of those manganese, right? And so if we make that MnH2, what coefficient should we put in front of this hydrogen?
2.
It should be a 2, right? Because that's supposed to be MnH2. We've just split it up into its pieces. And if that's a 2, then we need to balance this out over here. So this one needs to become a 4 now. So now all of our hydrogens are balanced. But there's something that's missing in our reduction equation. What don't we have in this reduction equation that we still need to add in?
The amount of electrons?
The amount of electrons. So are those electrons going to be products or are they going to be reactants?
They'd have to be reactants.
Reactants, right? Because we need to add them in. So for the Mn, how many electrons does it need to go from Mn3 plus to Mn2 plus?
Just 1.
Just 1. So that's 1 electron there. For these 2 hydrogens here, how many electrons did they need?
4. 6.
So each one hydrogen atom needed 2, and there's 2 of them. So how many did we need for that?
2.
We need, so each one atom needs 2 electrons, and we have 2 atoms of this
1.
H. So we have 2 atoms, and
4.
each of those atoms need 2 electrons.
4.
So we need 4 electrons, right? And so that's kind of going on to this one. So let's see.
Oh, I see.
So we need 4 electrons here. And so for the hydrogen that's going to the gas, each of those hydrogens need 1 electron, and there's 2 of them. So how many total electrons does it need to make that hydrogen gas?
Two.
It needs 2. So total, we need to transfer 1 plus 4 plus 5 and 6. Or so 1 plus 4 is 5 plus 2 is 7. So we need 7 electrons in order to transfer it.
Professor?
Mm-hmm.
So for the oxidation reaction, you had the product as CO2, but how come the product of the reduction reaction has manganese and hydrogen separate? Wouldn't it be the
So you have to look at your
MnH?
states, right? So if our MnH2, if we're treating it like it's aqueous, then
Oh.
that's how we split them apart.
Oh, okay.
Mm-hmm. Whereas if they were a gas, then we would leave them together, or a solid, we would leave them together.
Okay, I see.
Okay.
All right, I have to go now.
Mm-hmm. So this is how you would write out your half reactions. From there, we need to start to balance them. So we got the 7 electrons because we looked at how many each of those elements needed to change for each one, right? So we had 1 from this 1 electron. Then we had 4 from here and 2 from there. And so that's where the 7 electrons came from. Right? So from there, what we would need to do is we could balance them based on how many electrons are going to be transferred. So it's a little bit tricky because we would have are 8 electrons here, and we have 7 electrons here. And so there's not really a shared common denominator there, but that's normally what we would look for, right? Is if there was something that they both go into. And so 8 and 7, what number do they both go into? If we wanted to balance them for our 8 electrons that we transfer here with our 7 electrons down here, what do they both go into? What number do they both share? 56, right? So 8 and 7, they would both share our 56. And so we could scale them up by multiplying this whole thing by 7 and this whole thing by 8, and we would get to our 56 electrons. So in a normal reaction, then that's kind of what you would be looking at, is that you would have however many we're oxidizing and however many we're reducing, and we're trying to get those to balance. Now, in this specific case, it's a little bit different because did we only have one species that was reducing? Do we only have one species that's reducing?
No.
No, right? So because we don't have just one species reducing, then we can actually have some more flexibility there. And so what I want you guys to do is we're going to take our balanced equation and we're going to update this. So instead of only looking at one Mn, how many manganese do we have from our balanced equation up here?
2.
2 inside of here and the 2 in front. So how many total?
4.
4. And then if we have 4, how many H's did we start off with?
$12.
12. And so I want you to go through and I want you to update both of these with our balanced equation. And then we're going to see how many electrons we transferred. So go back, look at our balanced equation up on top. I'm going to go ahead and clear out some of these things so that way you guys can see it a little bit better and go from there, okay? So as you guys start to fill these in, how many total electrons should we have transferred for this top one now? If we have 6 of these oxygens and 3 of these carbons going to 3 CO2, how many electrons does that whole process give away now? Do you guys kind of get what I'm asking, or are we a bit lost?
Do we just add up the total number of electrons on the reactant side?
So kind of yes and kind of no. It's now, when we had this before, and this was a 2, and this one was a 1, and this one was a 1, we had 8 electrons there. But now that it's scaled, right? Now that we're using the 6 and a 3 and a 3, how does that impact the number of electrons transferred? Is it still going to be 8, or should that change?
It's going to change.
It's going to change. And so what should that number now be if it's going to change?
$24.
24, right? So now this one has changed itself. So instead of being 8 electrons, we're up to 24 electrons. And so what did you guys get transferred for this whole big mess down here at the bottom? And so one way to do it is to go through and look at each one. So for our manganese, we had 4 of them, and each one needed 1 electron. For this one here, we have 8 of them, and each one needs 2 electrons. And this one here, we have 4 of them, and each one needs 1 electron. How many total electrons does that come out to? We have 4 of them, and each one gets 1 electron, so that's 4 electrons here. We have 8 of those hydrogens, and each one needs 2 electrons, so that's 16 electrons. And we have 4 of these hydrogens, and each one needs 1 electron. So total, how many electrons did we need? Yeah, we have 4, we have 16, we have another 4. 24. So we needed 24 electrons total. Now, how does that compare with our electrons that we needed for our oxidation? They should be the same. And so that's what we're looking for. And in a really well-balanced equation for a redox reaction, so that's something that reduces and oxidizes, our electrons transferred should be equal to each other. And so in this reaction, we have 24 electrons being transferred. And so that's kind of a review of all of our oxidation states, right? So it does a reduction, our oxidation. We did a little bit with the half reactions. Now, for our class, half reactions are not as big of a focus, right? But making sure that you can tell who's oxidizing, who's reducing, how many electrons are being transferred, right? So finding out that you had 24 electrons being transferred, being able to identify oxidation numbers. Those are all the really big important things. If you watch videos online, there is also another topic where they talk about balancing them inside of an acid reaction and a base reaction, right? To balance those different half reactions. We're not going to have as big of a focus on them yet. That's something that we might look into a little bit later on when we get into acids and bases over in chapter 12, right? So that's something that we kind of loop back into. Does anyone have any questions on oxidation and reduction before we move on? So we're not going to do another problem like that today, just because we're kind of limited on time and there's other topics that we need to cover, right? Okay. So another topic that people are seem to interested in is your ideal gas law stuff. Now, ideal gas law is a very big topic, and so that's why there's been so many worksheets on this. So if you haven't done that gas demo, right, where I recorded myself recording a reaction, and there were like 2 pages of calculations that you guys could work up, one with the zinc and then one with the magnesium, that's definitely something I would recommend that you do. Right? There's also 2 other practice worksheets that we had in there. So you want to make sure that you review those if you haven't. Right? But for a gas type of problem, our simplest one could be something like we started a reaction. And captured the gas produced at 25 degrees Celsius and the pressure of 764 millimeters of mercury. The volume of the gas was 126.4 milliliters. How many moles of gas was captured? Assume the gas behaves ideally. All right. So that's our simple gas problem. And so whenever we get something where we're dealing with gases, what equation should come to mind? PV equals nRT, right? That's something that we always want to keep around, especially if you have something where it's like behaves ideally or it's an ideal gas, anything along those lines, we want to be thinking about that. All right. Now, the second part of that, as you get a word problem with this, you want to start writing down some of that information that comes up. So we have a pressure here, which is 764 millimeters of mercury. We have a volume, 126.4 milliliters. We have a temperature, 25 degrees Celsius. Now, what are we solving for in this equation, in this question? What is it asking us to look for? Moles. So we're looking for N. So we want to rewrite that equation to solve for N. And so what does that new equation look like? So we want to bring this RT over onto the other side. So we should get N is equal to PV over RT. Very good. Now, before we just start plugging that in, what do we need to do to all of our measurements?
You have to convert them.
We have to convert them, right? And so the reason why we have to convert them is, what does R stand for? Not just the value, but what does it actually mean? R has a name. What's the name of R? It's the ideal gas constant. So it's a constant. And what it does is it's allowing us to transition from our different units into another unit. And so it's a constant. So that's in the same way that 12 inches into 1 foot is a constant. That is what R does, is it allows us, right, to transition from liters, atmospheres, and our K and our mole. Now, you can use 0.0821 as your constant as long as you have less than 3 significant figures for your values. If you have more significant figures than that, then you shouldn't be using 0.0821. We should go out, be more precise, right? So you really want to make sure that you're using the best constant that you have. There's actually one that's even farther out than that, right? In order to make this conversion. So what do we need to change our pressure into?
Atmospheres?
ATM, very good. So we need to divide that by 760. And so that becomes 1.00526 atmospheres. And how many significant figures should we record that to? Three. So 1.01 atmospheres. What should our volume be?
Liters?
Liter.
Liters. And our temperature?
Kelvins.
Kelvins. Right? Now, this is the most common mistake that we see for our ideal gas is that we start to just plug it in into the equation and we forget about the units. So you really want to make sure that you adjust your units in order to get them to match. You can't use R if you're not in the right units. Now, the nice part about that is you don't have to memorize anything. You just need to look at your equation sheet and it has your units there. So it should help you make that adjustment, right? The other part is that 760 that you guys use to get into your atmospheres, that is exact. So you don't have to worry about it only being two significant figures. It is an exact transition or conversion. So now that we have our pressure, volume, our R, and our temperature in the same units, we can now start to multiply those. So we have our pressure, 1.01 atmospheres. We have our volume, 0.1264 liters. And so make sure that you're dividing by 1,000, not multiplying by 1,000 when you're going from milliliters to liters. Otherwise, you're going to end up with too large of a number. This is 0.08206 liter atmospheres K mole. And our temperature is 298 Kelvin. Now, the reason why I like to include my units is so that way I can get the joy of crossing them out. So my atmospheres cancel with my atmospheres, liters with liters, and my kelvins cancel. And so we're ending up with just moles. Right? Now, for our volume, right? Because some of you guys are sending me volumes. It should not be 126,400. That is too big. And the reason why it's so big is because you didn't divide by the 1,000 when you moved it in. You multiplied by 1,000 when you went from milliliters to liters. So remember that there's 1,000 milliliters inside of 1 liter, not 1,000 liters inside 1 milliliter. So you want to make sure that you fix that. Otherwise, your value is not going to be correct. And so we're going to get our number of moles. And so what value do you guys get? Now, how many significant figures should our value have? 3. Now, are those zeros that come before the 5, are those significant? Right? What do we call those zeros that come in before the 5?
Leading zeros?
Leading zeros. So are leading zeros ever significant? No, right? So we shouldn't be doing it as 0.01 or 0.005. Those each only have one significant figure. So instead, we should have that as 0.00522 moles. Okay. Any questions on that? All right, now let's say, well, if my gas sample weighed, oh, hold on, give me 1 second. Zero 0.20856 grams. What noble gas could it be? So we've captured this gas, we found the number of moles, and now I'm telling you its weight. So I would like to know what noble gas could it be? So I want you guys to go ahead and figure that part out. What noble gas could this be? So if it's asking us to ID something, what is a way for us to ID a material?
Molecular weight.
Right? So our molecular weight or our molar mass, right? So if we wanted to find our molar mass, how do we do that?
Grams over moles.
Grams over moles. So do we know the mass of our sample?
Yes.
0.2085 grams. Do we know the moles of our sample?
0.00522.
So what molar mass do we have?
$39.95.
39.95 grams per mole. And so what noble gas could that be? It's a pirate's favorite noble gas. It's argon. And so that's what we're looking for, right? And so this is why the ideal gas law can be so powerful, is there's a lot of information that we can pull out because it lets us take our gas and get us into moles, which we can then use for molar mass and things along that line. Does anyone have any questions about this kind of setup?
Nope.
Now, from here, there's another type of question, right? And it shows up in that it has several conditions. So it might be something where you start off with a sample is taken at 25 degrees Celsius and the pressure of 762 millimeters of mercury. It has a volume of 234.6 milliliters. The sample is then cooled to negative 124 degrees Celsius. And the volume is kept the same. What is the pressure of the chilled sample? So another type of problem looks a little bit like this. In that we have a lot of different things going on here. But we can't just use PV equals nRT. Because do we know the number of moles of our sample?
No.
No. So we can't just plug in PV equals nRT for our second set of conditions and try to identify what the pressure would be. But instead, they've given us like two conditions. They've given us one set that happened at 25 degrees Celsius. And then they're giving us another one that's at a lower temperature. Right? So it's the same sample under two different conditions. And so there's a different equation that we can use. And so what's that equation that we can use for this other one if we have two sets of conditions?
So it'll be P1V1 over T1 equals P2V2 over T2.
All right. And so what I like to do is I just include all of it to begin with, right? P1V1 equals N1T1, or is P2V2 over N2T2, right? And then what we can do is we can remove anything that has maintained the same. Anything that's staying the same is going to end up canceling itself out. And so this is called the combined gas law. And it works on the idea that they both have to, this equation, P1V1 over N1T1, is going to be equal to R, which is a gas constant. So if we have that same material at different conditions, this other P2V2 over N2T2 should still equal R. As long as our gas is ideal, those things are always going to end up being equal to each other. And so that's kind of the idea about how this works. So for this one here, what has stayed the same under our two conditions?
Volume.
Volume has stayed the same, so we can go ahead and we can remove that volume. What else has stayed the same?
Could we assume that moles stay the same?
Right? So if it's the same sample, do we think that any amount of material has been lost between those two things?
No.
No. And so yes, we can assume that our moles had stayed the same. So it doesn't have to explicitly state it. It's just one of those things that if we're reading through, if it's saying that's the same material, then we can assume that's the same amount, right? Now, if it had said, oh, under these new conditions, something has changed, what's the new number of moles in the sample? So let's say that we had a balloon, it was one volume at one temperature, and then we changed it to a different volume at a different temperature. We might want to look for how many new moles are inside of that, right? So looking at this, what we need to do is we need to update for our different sets of conditions. So it doesn't matter which one is P1 and which one is P2, but we need to make sure that they match. And so in this case, I'm going to take my 25 degrees Celsius and I'm going to make that our one condition, right? And my negative 124 degrees Celsius, that's going to be my second. So I am looking for P2. That's what I'm going to solve for. And so my equation is going to look like P1 times the temperature 2 over the temperature 1 is equal to my pressure 2. Now, can I just plug in those values as they are, or do I need to change anything to them?
So we would need to convert millimeters mercury to ATM and then Celsius to Kelvin.
Right? So when in doubt, always convert everything, right? If you're not sure, you can convert things back. But even if we wanted this in millimeters of mercury, it doesn't hurt to do that conversion. What we can do is we can take that 762, divide by 760. That becomes 1.00 atmospheres. We can take our T1, that becomes 298 Kelvin, our T2, and that's negative 124 plus 273. Now, when we plug that all in, we'll get our P2. So we get 1 atmosphere times 129 Kelvin divided by 298 Kelvin. I guess I should really put that as 1.00. And so our pressure 2 is 0.500 atmospheres. And if I multiply that by 760, we're going to get 380 millimeters of mercury. Is there anything that I need to add to that before I consider that my final answer?
I think either like, well, actually, I guess it depends on what units the question is asking for.
So let's say that we're asking for millimeters of mercury.
So then I guess we could also mention that it's the final pressure, or
Right?
So we would have to convert it back into mmHg, right?
Yep. So let's say that we have this up here as 380 mmHg. Is there anything else we should do to that? Or is it fine how it's written for our value?
I think it's fine because the question gives pressure and also millimeters mercury.
Right? How many significant figures is the 380 that we have written?
Oh, it needs to be 3 significant figures.
So it needs to be 3. So how could we express this so it would have 3 significant figures?
3.80 times 10 squared.
So we could do it that way. Is there any other way that we could write 380 so it would have 3 significant figures? That one has 4, Santina, but you're close. How does this change things? If I just put a decimal, apparently it took too long to write it. If I just put a decimal down there, how does that change things for us? Do we have 3 significant figures now?
Yes.
Yes.
Yes, right? And so that's what we could do. Now, what I would tell you about combined gas law is there's a shortcut that people use. And it's because if you are going from mmHg into mmHg, you actually don't have to do the conversion into atmospheres first. Because basically what happens is you divided one side by 760. So we took P1 and we divided it by 760, and then we took P2 and multiplied it back up by 760, right? So it kind of ends up being the same thing. But there's one unit that you always have to change, and that's your temperature. So you can never cut the corner and keep your temperature the same. You always have to change your temperature into Kelvin. And the reason for that is because we are just adding in that 273 on both sides. And so you'll get really funky results because 25 over negative 124 isn't the same as 149 over 298, right? Those values don't work out to be the same thing. Whereas 380 over 762 is the same thing as 0.500 over 1.00 when we consider our significant figures. So just be aware about that, is that your temperature always needs to be changed. We don't always have to change our pressures and our volumes, but when in doubt, change them. It never hurts to have them changed. Any questions on that? Any other questions about ideal gas law? So to repeat that, right? When in doubt, change all of your units, right? So what you want to do is you want to get all of your units into atmospheres, Kelvin, moles, and liters, right? When in doubt, change them. It might not always be the fastest way, but you won't ever have a mistake with your units not being in the correct ones. There are different shortcuts out there. So if you watch some videos, sometimes people won't change them. And that's because you don't always have to. But if you don't know when you can take the shortcut, always take the long way, which is convert all of your units. Okay. Any other questions about ideal gas law? Okay. So I do want to have you guys do one more big question before we head out of here. And that's going to be, not this one, a precipitation reaction. And so I want to go up to this one here. No, not this one. Let's blow this up a little bit. And so what we want to do from here is we are going to take a solution. We're having our ammonium sulfide and our copper nitrate. We're going to react them together. We're going to produce a precipitate. And we want to know the concentration of ions in that copper nitrate. So I'm giving you this equation up here. Actually, we can clean this up a little bit. What I want you guys to do is to figure out what was the concentration of our copper ions, so just the Cu, in our original solution. You can assume that all of that copper ion, right, all of that copper has been extracted when we make that precipitate.
Does this involve writing the complete ionic equation and then finding like moles per liter?
So it can, right? At the end of the day, there's like two different pathways of how you can kind of figure out what's going on. You don't necessarily have to have the net ionic or the complete ionic, but you do have to understand what's kind of going on for that precipitation. So I'm going to go ahead and I'm going to break you guys into two breakout groups so that way you guys can work on this a little bit. So you want to make sure that you've written down the equation so that way you guys can get started with it. All right. So I want you guys to think about it. But basically you have these two solutions, you're mixing them together, you're forming a precipitate. That new precipitate has this mass, 0.3491 grams. And so we want to know the concentration of it in its original solution. So we're going to let you guys take that, take a shot at that. Did you guys get a chance to write down the problem, or do you guys need me to share it with you guys?
Could you share it, please?
So if you want, you guys can take a picture with your phone, like screenshot it, and then you guys can hold on to it that way if you want. Otherwise, I'll leave it up for a couple minutes, and then I need to jump over to the other class to check on them.
I wrote it down. Thank you.
Okay. Anyone else still need it?
No.
Okay, you guys. Good luck. I'll check
Yeah,
back
that's
in
good.
with you guys in a couple minutes.
Sounds good.
Yeah, you guys, were you able to write down the problem, or do you guys want me to share it with you?
I have it.
Okay. Does anyone else need it?
What was the question we're trying to solve for?
The question is what is the concentration of the copper ions in the original solution? Okay. So we're looking for the concentration of the copper ions in that original solution. I'll let you guys work on that for a couple minutes and then I'll check back with you.
Okay.
We'll divide by liters or volume.
Very good. So we're going to change that into our molarity. So that's kind of the pathway of what we need to accomplish as we're going through. Now for your guys' exam, this is going to be in person, and so our exam looks a little bit different than what you might see on the Canvas question. So a Canvas question would look more like what we just had up on top, and you're kind of trying to accomplish all of that. For your in-person exams, then there's a little bit of help or scaffolding along the way, so you want to make sure that you fill in those questions as you go, right? And so it's asking us for the moles of our copper sulfide, so we can turn that into moles of the copper nitrate that's required, and then we can get to the molarity of the copper ions. So it kind of works your way through a little bit. So in some ways it can be helpful, it gives you some scaffolding, but in other ways you want to make sure that you figure this part out. So this document's not up yet, right? So this is still something that I'm piecing together, and then I will put that up in your exam number 2 review, which should go up hopefully tomorrow, okay? So looking from this, right? We already have our copper sulfur. So we know that that's 0.3491 grams of CUS. And so if I want to get that into moles, what do I need to use?
AMU of CUS.
Right? So we need to use the molar mass of our copper sulfide, right? So 1 mole of CuS is how many grams?
95.612.
95.612. Very good. So now that we're in the moles of the copper sulfide, how can I change that into the moles of the copper nitrate? What do we use for that?
Mole to mole ratio.
Mole to mole ratio. So in this example, is our equation balanced? Is this equation balanced?
Yes.
Yes. And so we can use its coefficients for the ratio. And so if we have 1 mole of copper sulfide, how many moles of copper nitrate would we have needed?
1.
1. Very good. Now, when that copper nitrate dissolves in that solution, how many copper 2 plus ions does it make? What should its mole to mole ratio be for the copper nitrate and the copper ions in solution?
Is it Avogadro's number?
Avogadro's number is the number of molecules in 1 mole, right? But we're still doing moles and moles. So do we need to use Avogadro's number?
Probably not then.
No, so we don't need to use that. But if we have 1 mole of CuNO32, how many moles of Cu2 plus would that make when it dissolved or disassociated?
Is it half because Cu2 plus and then it has to consider the sulfide as well, or
Right? So if you have 1 of these, that should make 1 copper nitrate and 2 NO3 minuses. So our ratio should still be 1 to 1. It's still going to be 1 mole of copper nitrate makes 1 mole of copper 2 plus. It would be different if we were talking about our nitrate ions, because that would be 1 mole of copper nitrate makes 2 moles of our NO3 minus. And so that's where that ratio could vary, right? So we want to make sure that we're paying attention to what actually happens when it disassociates inside that solution, right? So it's a 1 to 1 ratio for the copper, but it would be a 2 to 1 ratio for the nitrate to the copper nitrate. So we could do all of that there. And what this is going to find out for us is our grams canceled, our moles canceled, our moles canceled. We're going to find out our moles of our copper 2 plus that was in solution. So we got 0.3491 divided by 95.612. 0.00365. Oh, we need one more. 1 moles of a copper 2 plus. And so if we want to change that into a molarity, what do we need to divide that by?
so we need to find out the volume of copper ion.
Right, so we need to find the volume. So looking at our original solution, what was the volume?
Uh, 0.15 liters.
0.15 liters, right? And that's because the copper nitrate is in this solution here. The 20 milliliters was the one with the sulfide. So this becomes 0.1500 liters. And we want that in liters because we want the molarity. So we divide this by 0.15. And so we should get a concentration of 0.02434 molarity of our copper nitrate, or sorry, of our copper ion. And so that's what you're looking for something like that. Anyone have any questions on that?
Is there like some sort of way that we can practice the this type of like
So these
this
ones are
dimensional
called
analysis?
precipitation problems.
Okay.
And so what I would recommend, right, if you want more of these, is there's a lot of them at the end of your chapter 4 book, right? And so that's where I would look for some more of them. Okay. So kind of like those extra practice problems at the end of chapter 4, that's kind of where I would look for some of them that look like this. You can also redo your Connect homework because it's been a couple weeks since you've done it. And so you could work your way through some of those type of problems as well.
For sure.
Any other questions? So we got through a lot today. Reminder, there is another session tomorrow morning. So we can do some more. We'll be moving on past ideal gas law and we'll be moving into your thermochemistry, right? We also have a review session on Wednesday. Wednesday, we'll cover the end of chapter 7 and chapter 8, as well as we'll have some more leftover time. So if there's other materials, like you guys want to see more of these or other ideal gas law problems, things like that, then come with your problems and be prepared. And then we'll go over those on Wednesday, right? If you come in with specific problems, we'll also get through more of those questions. So if you guys have something in particular, you can always send them. I check the announcements for that, and then we'll get through that. Okay.
Also, my bad. By the way, I had biology earlier, but is tomorrow's session, does that begin at 8 a.m.?
So tomorrow's session, let me look at what time it starts at.